this is chapter 5, boiling and condensation. So for this video, I will focus first on boiling, and after that, the next video will be condensation. So basically, this chapter is chapter 5.1 for boiling. So objectives of this chapter, not 5.1 and 5.2, but overall for chapter 5. So when you finish studying this chapter, you should be able to, one, differentiate between evaporation and boiling, and gain familiarity with different types of boiling. And second, develop a good understanding of the boiling curve and the different boiling regimes corresponding to different regions of the boiling curve. Third is calculate the heat flux and its critical value associated with nucleate boiling, and examine the method of boiling heat transfer enhancement. Okay, and last, calculate the heat flux associated with condensation on inclined and horizontal plates, vertical and horizontal cylinders or spheres, and tube bundles. Now, boiling heat transfer. So basically, there is two. One is evaporation, and then the second one is boiling, because we are learn about the boiling and condensation. So now, under the evaporation, occurs at the liquid vapor interface when the vapor pressure is less than saturation pressure of the liquid at a given temperature. So, for example, the saturation pressure for a water in a lake at 20 degrees Celsius, okay, evaporates to air at 20 degrees Celsius, and 60% relative humidity, since the saturation pressure of water at 20 degrees Celsius is 2.3 kPa. And the vapor pressure of air at 20 degree and 60% relative humidity is 1.4 kPa. So which means that if the vapor pressure less than the saturation pressure of the liquid, it will evaporate. And evaporation basically happens at the surface, on the surface of the liquid to vapor interface. So which means the interface of liquid and vapor will occur, the evaporation will occur. So what about the boilings? Boiling occurs at the solid liquid interface, as you can see in the figure. So the evaporation will happens or will occurs at the liquid and vapor interface. So it will evaporate the water inside. Okay, here we have figures of water at 20 degrees Celsius, and at the surface of this water, it will evaporate to the air. And then whereas for the boiling here, so if we are continuously supply the heat at the bottom of this kettle, so what will happen is actually the boiling will occur in the water, where the boiling is usually occurs at the solid and liquid interface, which means that if I draw the if I can increase this figure, so the boiling will occur. This is the bottom of the kettle, and then this is where the continuous heating here. So this is water. So the boiling will occur at here. So solid and liquid interface. So the rate of heat transfer will occur at here. Okay, when a liquid is brought into contact with a surface, maintain at the temperature sufficiently above the saturation temperature of the liquid. So for example, we take the water at pressure of 1 atm, and normally pressure at water at 1 atm and water at 1 atm the saturation, T saturation for water is at 100 degrees Celsius. So which means boiling will occur if you supply the temperature here, heating, at the temperature above the saturation temperature. For example, you are heating up the water in this kettle to the you supply it with a temperature of 102 degrees Celsius, for example, or maybe you want to supply with 120 degrees Celsius, and then the water will boil because the saturation pressure and saturation temperature for the water at 1 atm the saturation temperature for water at 1 atm is 100 degrees Celsius. So this is 120, and then you have in excess of 20 degrees Celsius. Therefore, the boiling will occur in the water. Okay, so that is boiling. So the classification of boiling, there are two classifications of boiling. First is pool boiling, where the boiling is called pool boiling in the absence of bulk fluid flow. So, for example, we are heating water in a jug, in a kettle or in a pot. So that is a pool boiling. So any motion in the fluid is due to natural convection currents and the motions of the bubbles under the influence of buoyancy. So which means that when we heat up this water, this kettle or pot, what will happen is the natural convection will occur in the water. So which means that the hot water will goes up, and then the cold liquid will replace that position, and then it will continuously occurs, and then this is the effect of buoyancy. Where we know that the fluid which has high temperature, it will goes up, and then liquid with low temperature or cool temperature, and it will move and fill the vacant space that left by this hot fluid. Okay, this will occur continuously. This is what we call as a natural convection currents. Okay, the motions of this fluid inside this system. Okay, so for the flow boiling, okay, boiling is called flow boiling in the presence of bulk fluid flow. In flow boiling, the fluid is forced to move in a heated pipe, or over a surface by external means such as pump. So which means that the flow boiling will occur in the bulk fluid flow. The fluid will flow inside this pipe by the helps of pump or external force. Okay, so this liquid, we call these particles, will move from here to that position by the means of external force, convection, external force such as pump. Okay, that is flow boiling. So basically for this chapter, we are focusing more on the pool boiling. So where we have a kettle, and then we heat up the kettle, and we will examine or trying to understand about how the boiling occurs in that fluid. Okay, so the classifications of boiling, we have another classification where we have subcool boiling and saturated boiling. So for the subcool boiling, when the temperature of the main body of the liquid is below saturation temperature. So for example, here we have two different figures here. For this one, we call it as a subcool boiling, where we have the temperature of fluid inside this kettle is at 80 degrees Celsius. And then we know that the temperature, for example, water at 1 atm, it will boil at 100 degrees Celsius. Okay, saturation temperature of the water is at 100 degrees Celsius, and then this water has 80 degrees Celsius, which below than the saturation temperature of the water at 1 atm. Therefore, this is what we call as a subcool liquid. Subcool boiling. For the saturated boiling, when the temperature of the liquid is equal to the saturation temperature. So take a look at the liquid here, 100 degrees Celsius. For example, we take water at 1 atm. So water at 1 atm, the saturation temperature is 100 degrees Celsius. So here we have liquid at 100 degrees Celsius. So in this case, we call it this as a saturated boiling. So that is the definitions of subcool boiling and saturated boiling. So what is much more important for you in this boiling subchapter is to understand about these figures. These figures is water at 1 atm. Okay, this graph, these figures is for water at 1 atm. So as we can see here, we have y-axis is q dot boiling. Yeah, heat flux. Small q dot boiling is a heat flux. Okay, and then we have here is delta T excess. Okay, we have 5, 10, 30, 100, 120, and 1000. So here in this graph, okay, in this graph we have 4 different regions. First region is natural convection boiling, and then we have nucleate boiling, then we have transition boiling, and then film boiling. So I will explain one by one of this region because we have to understand about this figures before we can do our calculation in the boiling. So what you have to remember, your job here is to memorize these types of figure. So please remember everything that is in these figures. Okay, for example, you do not have to draw these kinds of figure. You have to draw the q dot boiling, the y-axis, and then you have to know the delta T excess, and then you have to know about the natural convection boiling region, nucleate boiling region, and transition boiling region, also film boiling region. So here we have natural convection boiling, where the region of the natural convection boiling is below than 5 degrees Celsius. So bubbles do not form on the heating surface until the liquid is heated a few degrees above the saturation temperature. So here about 2 to 6 degrees Celsius. So at this point, there is a natural convection occurs inside the fluid. So buoyancy, and it will replace. So if at this point, so what will happen is the fluid, okay, I put it dot here. So the fluid at the surface of this pot, at the bottom of this pot, what will happen is this fluid will be heated up, and then it will reduce the weight of that fluid, and then this fluid will move up, and then the other fluid, which cold fluid, will replace the positions of this liquid, and it will continuously occurs up to excess temperature of 5 degrees Celsius. So here is delta T excess. So you have to minus T surface of this, here is T surface of this pot or kettle or this surface, and then minus with T saturation. In this case, at 1 atm, water will boil at 100 degrees Celsius, which means that this is excess of 5. Okay, so below than this, natural convection boiling occurs. Okay, so the first bubbles start forming at point A. So here we have another region. When it reached 5 degrees Celsius, or you heated up your water in excess of 30 degrees Celsius, it may experience the nucleate boiling, where we have two different regions here. So A to B and B to C, we have two different regions. So for point A is referred to as the onset of nucleate boiling. The bubbles form at an increasing rate at an increasing number of nucleation sites as we move along the boiling curve towards C. So it will rapidly form bubbles at the bottom of this pot. So what will happen is actually at point A, it will start, if I can draw a little bit bigger here. So what will happen when we continuously heat up, and then the excess of the temperature is 10. So the bubble will form at the bottom of this kettle. So what will happen when the bubble is sufficiently or the pressure inside this bubble is increased, okay, it will goes up and it will form a bubbles. Okay, these bubbles will collapse, okay, will collapse inside of the water, inside of the fluid. Why? Because now the fluid is at 100 degrees Celsius. The temperature inside this bubble is basically higher. The temperature is basically higher than the temperature of the fluid. Okay, when the temperature is higher, pressure is high. For when the pressure is high, at sufficient level of these bubbles, it will increase, and then at sufficient level, it will collapse. So when it collapses, it will transfer the heat to the surrounding. Okay, the bubbles will rise and then it will collapse, and that collapse will transfer the heat to the fluid. Okay, this is a continuous process, and then when the bubbles is rise, there is another bubbles will form at that position, and it will continuously, because we know that we have a natural convection process where the cool liquid will replace. Let's say we have this, we have bubbles here. When these bubbles rise, and it will vacuum the space, and then another liquid will fill up that space, and then that space fill up that space, and it will form another bubbles, and it will continuously form, okay, until it reach to the points of C. Okay, point B to C, the bubbles will rise to the free surface. What will happen when the actions of collapse, the action of burst of the bubble burst inside the fluid? What will happen? It will transfer the heat to the surrounding, to the fluid actually. Okay, it will transfer to the fluid. What will happen when this temperature of the fluid outside, temperature of the fluid is basically same as the temperature of the bubbles, then the bubbles will not collapse inside of the fluid. It will rise up till the free surface here, and then it will collapse at the surface of the water or the fluid. Okay, it will rise up to the free surface and collapse. So this action normally our mom always call it as menggelegak. So that is why we see a bubbles collapse at the surface of our fluid of water, at the surface of our water when we boil a water. Okay, so we can see these kinds of formation or these kinds of phenomena when we boil our water in a kettle, okay, or in heater. So when this when these bubbles will form, and there will be more nucleation site. Nucleation site is this nucleation site of the bubbles. So maybe at the beginning A, it will form only one side. For example, okay, for example, maybe it will form at here. So after increase in temperature, as you can see, the excess temperature is increasing. So what will happen? There will be more nucleation site on the surface of this pan, and then it will form many bubbles, and then the heat transfer will occur, and after sometimes it will rise to the free surface and collapse, because it cannot collapse inside this fluid anymore, because the temperature inside of this fluid is the same as the temperature for the vapor. So, and after that, the act of continuously continuously form the nucleation site, what will happen at this point C, we have a maximum heat flux, Q dot maximum. So Q dot maximum occurs at approximately delta T excess 30 degrees Celsius. Okay, what will happen at this point? So at this point, because so many nucleation site occurs or develop on the pan surfaces, it will actually develop a film here. So when there is more nucleation site, and it will form a film, all those sites will combine, and then it will create a film here. So what will happen when it creates a film? When we increase the delta T excess, the Q boiling will be reduced. This is what we call as a transition region, where there is a film here. Increase in temperature will reduce the Q boiling, because at this point, okay, the vapor film here, when there are more bubbles, nucleation sites occurs at the pan bottom, and what will happen? It will create a vapor film. So this is vapor film. So this vapor film act as insulation. So when there is a heating, when there is a heat supplied, so this vapor film will act as insulation. So why? Because the thermal conductivity for the vapor film is much more lower than conductivity of liquid. So because of this thermal conductivity of the vapor film is low, that it acts as insulation. Okay. So when acts as insulation, the Q will not rise up, and it will reduce up to the point where we have here minimum Q dot boiling. This is minimum heat flux. We call it as Leidenfrost point. Okay. So Leidenfrost point is a minimum point in honor of Jesse Leidenfrost, who observed in 1956 that liquid droplets on the very hot surface jump around and slowly boil away. The presence of the vapor film, so this vapor film, between the heater surface and the liquid is responsible for the low heat transfer rates in the film boiling region. So here in the transition region, it will reduce the Q dot because of the vapor film. So vapor film is low in thermal conductivity, therefore it will act as insulator. Okay, the heat transfer rate increases with increasing excess temperature as a result of heat transfer from the heated surface to the liquid through the vapor film by radiation. So if we increase up the delta T excess or the temperature surface, okay, or delta T excess, from 120 we have the leaden frost point, the minimum heat flux. So after that we have film boiling. At the film boiling region, this graph will increase back. Okay, why? Because at this point there will be no convection occurs, and that convection will change into the radiation process. So these, when we heat it up, at first we have the convection process from the natural convection boiling and the nucleate boiling up to the maximum critical heat flux. So after that, the vapor film form. The vapor film is low in thermal conductivity. What will happen? It will act as insulator. So that's why the boiling, Q dot boiling here will reduce to the minimum value. This is what we call as a latent frost point, Q minimum. Okay, and then after the transition boiling, so we will see that the graph of the Q dot boiling increase after the minimum value, minimum heat flux, latent frost point at 100, approximately at 120 degrees Celsius delta T excess. So at this point onward, okay, at this point onward, this is what the convection mode here from the natural convection boiling and nucleate boiling will convert to radiation. So here the vapor film will radiate the energy and it will transfer to the liquid, okay, or the fluid inside of this the liquid inside of this heater or pot or kettle. So here the vapor film will radiate the energy to the liquid inside of this pot, okay, heater. So a typical boiling process does not follow the boiling curve beyond point C, and we can see that Nukiyama has observed. Nukiyama has observed during his experiment. Notice this Nukiyama is researcher. He do the experiment, and then he noticed that with surprise that when the power applied to nichrome wire immersed in water exceeded Q dot maximum, okay, which means at this point C we have maximum heat flux. Nukiyama observed when more heat, okay, transferred to the nichrome wired that immersed in water exceeded Q max. What will happen? Wire temperature increase suddenly to melting point of the wire at 1500 K. So which means that the boiling curve the boiling is only occurs until up to the point of C. If we increase more the delta T excess, it will increase the temperature of the electrical heater. That heater, or in this case Nukiyama use nichrome wire. What will happen? The nichrome wire will increase its own temperature up to the melting point of the wire, which is 1500 K, and burnout occurred beyond his control. Okay, when he repeated the experiment, he does not believe that nichrome wire turns to be like that, and he repeat that experiment with platinum wire. He do not use nichrome wire, he used platinum wire for the next experiment, which has a much higher melting point. So because before this, nichrome wire melt at 1500 K, and then he changed the wire to the platinum wire, where platinum wire have the higher melting point, 2045 Kelvin. He was able to avoid burnout and maintain heat flux higher than Q dot maximum. Okay, if higher than Q dot maximum, when he gradually reduced power, he obtained the cooling curve shown in figure. Okay, with a sudden drop in excess temperature when Q dot minimum is reached. Okay, note that boiling process cannot follow the transition boiling part of the boiling curve past point C unless the power applied is reduced suddenly. So as we can conclude from the experiment of Nukiyama, Nukiyama summarized that the normal boiling process does not follows these figures actually up to the point of C to E, okay, C, D, E. So if we want to follow these kinds of graph, graph, so we have at point C to D, we have the minimum heat flux. So to get from C to D, we have to reduce the power, which means we have to reduce the temperature lah. Okay. And then if we increase, if we already reach at the maximum critical heat flux and we increase the temperature, okay, the delta T excess here, we increase the delta T excess here, what will happen? That what we call that wire, in this case Nukiyama used nichrome wire, will actually increase its own temperature up to its melting point, and then burnout phenomena occurs. Okay, so if we increase the temperature from C to E, so we have the maximum we can get, and the normal boiling can follows from A, B to C only. So if we increase more, then we have burnout phenomena. So here we have the burnout phenomena here. So Nukiyama do these kinds of experiment up to the point C, and then we know that Nukiyama used nichrome wire. What will happen if what will happen when he increase the temperature delta T excess here more than 30 degrees Celsius? What will happen? It will turn into burnout. That wire or electrical heater will melt, okay, because it will increase its own temperature until it reach to the melting temperature of that heater or that wire, and then burn out. It will jump to point E. So I believe that this point E is the melting temperature of wire. In that case, Nukiyama used nichrome wire and melt. And if we want to follow these kinds of shape or curve, we have to reduce the power. That is what Nukiyama told us. Okay. So actually what happened when burnout phenomena occurs? So burnout in boiling can be explained in order to move from point C, where Q dot maximum occurs, we must increase the heater surface Ts. Okay, here. In order for us to move beyond the point C, as we can see here, the point C is at delta T equal to 30 degrees Celsius. If we want to move further, we have to increase delta T excess, which means we have to increase TS of your heater, okay? And or in other words, we have to increase the power supplied to the heater, and then to increase TS, however, we must increase the heat flux, okay? When we know that when we increase the TS, so we will increase the TS, when we increase the TS, it will increase delta T excess. When we increase the delta T excess, we know that the Q boiling will increase, okay, Q dot heat flux. But the fluid cannot receive this increased energy at an excess temperature just beyond C. Therefore, the heater surface ends up absorbing the increased energy, causing the heater surface TS to rise. So that heater surface cannot increase the energy, and then end up that heater absorbing the energy, okay? And what will happen when that heater absorbing the energy, the TS for the heater will increase, okay, will rise. But the fluid can receive even less energy at this increased temperature, causing the heater surface temperature to rise even further, okay? This continues until surface temperature reach a point at which it no longer rises, okay? And the heat supplied can be transferred to the fluid steadily. This point E, okay, on the boiling curve, which correspond to very high temperatures. Therefore, any attempt to increase the heat flux beyond the Q dot maximum will cause the operation point on the temperature that correspond to point E is beyond the melting point of the most heated materials, and burnout occurs. So point C on the boiling curve is also called a burnout point, and the heat flux at this point, the burnout heat flux, okay? So point C is what we call as a burnout point, and the Q at the point C is what we call burnout heat flux, okay? So that is about these figures, okay? These are graph. So basically, when we increase the delta T excess, and it is impossible for us to get these kinds of graph, because from point C, it will jump to the point E. This point E is the point delta T excess where it is exceeded most at high temperature, and mostly it is exceeded to the melting point of materials. And what will happen, it will burn out or melt, okay? So the point C will directly move to point E, okay? So this is the definition, explanation of what I've already explained to you about the graph. So the natural convection to point A on the boiling curve. So what will happen at this region? The liquid is slightly superheated. In this case, it is a metastable state. Okay, the fluid motion in this mode of boiling is governed by natural convection currents. So then it moved to the nucleate boiling. So we have region AB, isolated bubbles, and then region B to C is numerous continuous column of vapor. So this is isolated bubbles, which means the bubbles is less at if we can see here. So if I take a look from top, so the bubbles will form on the surface of this pan or the heater, and then that is isolated bubble, and then it will rise, and that vacant space will fill up by the cool water. and then it will continuously occurs. And after the delta T excess is at 10 degrees Celsius, and then it will form more nucleation site, and then what will happen, it will form more nucleation site, and then continuous bubble will occur. So after that, until when there is more nucleation site occurs, it will form a vapor film. All this bubble will combine and it will increase. If I can show you at this side of the pen, and then it will form a vapor film. So this vapor film thermal conductivity is reduced because vapor thermal conductivity is lower. So when the thermal conductivity is low, then that is why there is a transition region, and then it will reduce the Q dot boiling heat flux up to the minimum temperature, down to the minimum temperature, and this minimum point is what we call as a, not minimum temperature, minimum heat flux. This point what we call as a Leidenfrost point. So the act of increase of delta T excess more than 120, and it will fall under the film boiling. So at this film boiling, what will happen is actually the radiation occurs. It will not use convection mode, but it will turn into radiation, where the vapor film will radiate energy to the liquid. Okay, so this is continuous column of vapor. So the vapor will continuously form, and then that bubbles will go to the free surface. So the nucleate boiling here is more on the definition or explanation on the nucleate boiling. Okay, so we know that there is a critical heat flux here, Q dot maximum. So after, sorry. So nucleate boiling at the critical heat flux, and then we move to the transition boiling. Okay, this is because last delta T excess is increased, past point C, the heat flux decreases. Okay, it will create, this figure shows the vapor film on the surface of the heater or the pan, and it will act as a insulator, and then the Q dot will reduce. So film point beyond point D, the heater surface is completely covered by a continuous stable vapor film. So point D, so this is point D, minimum Leidenfrost. Heat flux reach a minimum is called Leidenfrost point. So the presence of vapor film between the heater and surface and the liquid is responsible for low heat transfer. So as we can see here, the increment or the curve is the Q at this point is increased much low rather than this side. Okay, because of this heat transfer rate, low heat transfer rate. Okay, Q dot will increase slowly. Okay, the heat transfer rate increases with increasing excess temperature due to radiation to the liquid. So at this point, the film boiling, the radiation will occurs. It will no more convection process. Okay, radiation process will takes place in the film boiling because of the vapor film. The vapor film will continuously radiate energy to the fluid. Okay, this burnout phenomena, where previously I've already mentioned that the experiment conducted by the Nukiyama, where there is no curve here. And when Nukiyama use nichrome wire, what will happen? The nichrome wire will be nichrome wire melt. Okay, because from the point C, at the point C, the nichrome wire will gain an energy from the excess of the temperature, and therefore that nichrome wire will increase its own temperature, and then it will reach to its melting point. So that's why point C point C jump to point E. So mostly point E is the at high temperature, where mostly all the materials will melt at this point. So Nukiyama also concluded that if we want to follow these kinds of curve, we have to reduce the power of that wire or the heater. And at that experiment, Nukiyama used platinum wire. So he reduced the temperature, he reduced the power supply, and then there it will reduce these heat flux up to the minimum value. But at this point, as we can see, it does not reduce the heat supply to the wire, because the delta T excess is increased. Okay, what Nukiyama do is reduce the Q supply, and when we reduce the Q supply, we are actually reducing the temperature. So then we can get these kinds of figure, these kinds of curve. Okay. For a normal boiling, it is impossible for us to follow this. It is impossible for that heater to follow these kinds of curve. And normal boiling will only follow from this point, okay, this point up to the point C. Okay, if we increase the delta T excess, it will jump to the point E, where the burnout phenomena occurs. So we have the heat transfer correlation in pool boiling, as we can see here in the nucleate boiling. So this is nucleate boiling region. So we have these kinds of equation. Okay, this nucleate boiling, we have these kinds of equation. So you have to know the Q dot nucleate is mu1 mu L HFG G rho liquid minus rho vapor over the surface tension, and half CPL specific heat capacity for the liquid, and T surface minus T saturation, and CSF HFG and Prandtl number liquid power of N. This is nucleate region. So in the question, normally they will not mention about the nucleate region. So how can you understand that the question is asking you to use the equation in the nucleate boiling? So we have to calculate the delta T excess. So delta T excess here, you have to remember, okay, the range, the region here. So delta T excess for the natural convection is in between 1 to 5. And then for the nucleate boiling, in between 5 to 30. Okay. And then for the transition boiling, 30 to 120. And for the film boiling, 120 and above. Okay. Please remember this delta T excess. It is important. Okay. In the question, next week, you will see that the question will not state the region of that boiling. So it is you to determine where does that delta T excess falls into, okay, by calculating that delta T excess, and then you will use specific equation based on that delta T excess. For example, your fluid is at 120, 135, and then your T saturation, your water saturation, and you boil that water at 1 atm is 100, for example. And then 135 minus 100, you will get 35. So if I get delta T excess 35 degrees Celsius, where does this temperature delta T excess falls into what region. So we know that the region for the nucleate boiling is 30 to what? 32. Sorry. For example, your T liquid is 120, and then your water, you boil the water at 1 atm, and the desaturation for the water is 100 degrees Celsius. And 120 minus 100, you will get 20 degrees Celsius, delta T excess. So if we take a look at this region, 5 to 30, so your delta T excess is 20 degrees Celsius, and it falls under nucleate boiling. Then directly, you use the temperature, you will directly use nucleate boiling equation. So take out this equation and then substitute all the values given to you. Okay, and after this, in the example, I will explain a little bit more on CSF, CPL, rho liquid, rho V, and all of the information on from this equation. Okay, so in the example, I will explain a little bit more on how to calculate the Q dot nucleate. Next is heat transfer correlation in pool boiling. So nucleate boiling. So error for the heat transfer rate for a given excess temperature 100%. So now from that nucleate boiling, it will reach to the maximum heat flux. So that maximum heat flux, we call it as a critical heat flux. Okay, the critical heat flux, you will use this kinds of equation. Okay, Q dot maximum equal to CCR HFG. This is surface tension times with G rho V square rho liquid minus rho V. Okay, this is equation for the maximum heat flux. CCR is a constant whose value depends on the heater geometry, but generally is about 0.15. Again, after this, in the example, I will explain more on how to calculate by using this equation. Okay, so we know that after the critical heat flux, we have the Leidenfrost point. At that Leidenfrost point, the equation is this one. Okay, this should be Q minimum. Q dot minimum equal to 0.05 rho V HFG, surface tension G, rho liquid minus rho V over rho liquid plus rho V square. So the power of 1.1/4. This is for minimum heat flux, Leidenfrost point. Okay, this is the equation. Again, you have to determine the delta T excess. You have to minus TS, T surface, with your saturation temperature, and then you will get your delta T excess. And from delta T excess, you refer to the region of each of the boiling, and then you will determine where your delta T excess falls into. Okay, if it falls under the minimum heat flux, or in the question tells you that this is the minimum heat flux, so you directly use the equation for the minimum heat flux. Same goes to the critical heat flux. If the question asks you to find what is the critical heat flux for the boiling, for this boiling, so you have to directly use the critical heat flux equation. Sometimes the equation will ask you what is the temperature of the critical heat flux, or maybe temperature, normally temperature of the critical heat flux, for example. So you can actually equate, because this equation is the same as this equation. When this equation, you can see here, Ts minus T saturation. When the delta T excess, this is delta T excess, increase, and it will increase up to the point where it reached to the maximum heat flux. So you can actually equate this Q nucleate with maximum heat flux, critical heat flux, to get what is the temperature for T surface, for example. Okay. So for the film boiling, if you calculate the delta T excess and it falls under the film boiling, so you will directly use the Q film equation. Here is a Q film. Again, I will explain a little bit more on how to calculate by using this equation in the example. Okay, so this is for the horizontal cylinder or sphere. Okay, normally your pot is in cylinder shape. Okay. So this is enhancement of heat transfer in pool boiling. So the rate of heat transfer in the nucleate boiling regime strongly depends on the number of active nucleation sites on the surface. So we know that under the nucleate region, so there is more there is more bubbles form, and the more nucleation sites occurs on the bottom at the bottom of the heater or your pot. So what will happen, the modification that enhance nucleation on the heating surface will also enhance heat transfer. So these kinds of shape will actually enhance the nucleation. It will as we can see here, the nucleation site for vapors has been located here. So, and this will avoid the formations of the what we call the formations of the vapor film on the surface of the heater. Okay. So other than that, irregularities on the heating surface, including roughness and dirt, serve as additional nucleation sites during boiling. So that's all for the chapter 5.1 boiling. Thank you.